Hi everyone, welcome to the second day of the TOPML workshop 2022. After the successful day yesterday, today we have one more day with lots of interesting talks, great talks. Okay, so our first speaker today, our first invited speaker to start our wonderful day is Francis Bach. It's my great pleasure to introduce him. Francis leads the Sierra project team at INRIA in the Computer Science Department of Ecole Normale Supérieure. His research interests include many aspects of machine learning, including important contributions to the understanding of optimization and overparameterization in modern machine learning. Francis' talk is going to be a great start for this day and of the workshop. The stage is yours, Francis. Thank you very much.
So thanks, Yehuda, for the nice introduction and for the invitation. I wish it could be there live, but maybe the next edition will be live. So today I'm going to talk not really about the work of my group, but it will be like mentioned of what we do. It's mostly like a review of what machine learning is and maybe reasons for its success or theoretical reasons for its success. And the hope is being to push people to consider those aspects when they derive their new bounds for deep or shallow learning. So let me jump to it now. So I'm going to consider supervised machine learning with a classical formalization. So this is a classical setup of data xi, yi with n observations of that. And xi can be anything in some input space. Think of xi as an image or vector in RD, and yi some label, and binary label or real label, I think doesn't really matter. And in most of learning theory, people are considering that the data come from some source, the same source, independently and identically distributed. And this is clearly validity in many setups, but this is still a setup that people are using to analyze those techniques. Then we have a loss function, okay, characterizing if we do well. So if you give me y, the true label, and y hat, your prediction, L of y hat will be the penalty that you pay. So you want to minimize that. And the criterion, okay, the goal is to find some prediction function f that goes from inputs to outputs, so that the expected risk, so the expectation of the same distribution that was generating your data of the loss between the label and the prediction, okay, you want this to be as small as possible. Okay, so this is what you try to estimate in papers when you do test accuracy. Okay, and this is if you have a lower number, you're happy. So we know what the optimal prediction function would be. And when we say we know, it's in quotes because it requires full knowledge of the problem. And this is simply the so-called Bayes predictor or the target function f star, which is obtained by considering the conditional expectation of labels y given x and minimizing the loss function. Okay, so if you do, to make things concrete, if you do regression with a square loss, the target function is simply the conditional expectation of y given x. If you do binary classification with the logistic loss, you obtain as the log odds ratio and so on. Okay, so the goal of learning essentially to find that conditional expectation. So we know the solution. Okay, so the goal, of course, is to achieve a similar risk to the optimal prediction function. So some problems have a small r star or easy, so close to no noise. Some are hard, and the goal is to do as well as the best. So there are classically two types of learning algorithms that people consider. There are many others, but many of them can be put in one of these two categories: local averaging and empirical risk minimization. So let me go over them quickly and see what their behavior can be. So local averaging is very simple. Okay, since we know if we knew P of y given x, we could get the perfect predictor. those techniques are essentially estimating P of y given x with a formula. And then from that formula for P of y given x, they compute the expectation. So classical example is K nearest neighbor. So here this is for classification. So you have data, okay, in R2, you have like the squares, you have the circles, okay, this is a new point, okay, and you look around either at a fixed distance or the K closest point, and you do a majority vote. So can Engar close his microphone, please? So you do a majority vote among the points if you do classification. If you do regression, you do like the average over the closest point. So you can catch this as estimating P of y given x for that particular x. Okay, and so the good thing here that there's no training. Okay, so you just look at the data and get your prediction function, and there is still one hyperparameter that will determine how local you are. Okay, this is the number of neighbors if you do K nearest neighbor. This is the distance if you do kernel regression. So this is like very classical. The other class is ERM. So the principle is very different, but also quite simple. So you have data. So let's try to minimize the error on the data. And let's call that R hat, the empirical risk, the average over the data of the subloss. Of course, to optimize, you need to parameterize your functions, linear models, neural nets, okay, and then you minimize this. So for this, you need some form of capacity control, the idea being that if you get zero loss on the training data, this may not mean that you have a good performance on unseen data. You may have strong overfitting. And there are typically two types of capacity control. The classical one, where you constrain, you penalize some norm of the parameters. Or if you run some specific algorithms, so I will not talk about it today too much, but if you run gradient descent, typically you get a minimum L2 norm solution. So there's always, not always, but there is, in many cases, some norms hiding behind the scenes to do some capacity control. And of course, if you have a norm, you have one hyperparameter telling you how big and how small that norm can be. Now, of course, now there is some training, so you have to optimize this empirical risk. So this gives us a job, which is good, but then it can be quite slow. And of course, speed could be an issue. And also convergence, the global optimum can also be an issue. Okay, and I'll come back to that in a moment. All right, so now we have the two sets of algorithms that are classical. First, let's look at what we can say about those. So first, some bad news. Okay, so no free lunch theorem. So this is taken by the classical book by Devoy, Lugosi, and Murphy. And so you take like very simple problem, binary classification, any input space. And if you consider all potential problems, learning problems, if you take some that data dn from the distribution P, so dn depends on P, then what you can show is that if I take any decreasing sequence, okay, an, and let's take it decreasing to 0 very slowly, like 1 over log n, then if you give me any algorithm, okay, give me yours, okay, your super deep net or super shallow, whatever you prefer, then I can find the problem on which you will do, you could converge to the optimal solution, but at a speed that could be arbitrarily small. Okay, so this is one instance of a no free lunch theorem. And so what you get out of it, I think to me the take-home message that all learning algorithms must have some weaknesses. Okay? There is no universally good algorithm. Okay, so some work better than others, but this depends on the data. So you see the positive spin on the no-free-lunch theorem. People would say that, yeah, but that set of distributions, like there exists a P, but that particular P is very, very weird and unlikely to happen. Okay, so I agree with that. And this is why people start to focalize on sub-problems. And in this talk, I will focalize not on any X infinite, but X in RD. Okay, so I'm going to consider data in RD. And now in RD, the no free lunch theorem is essentially transferring into what people call the curse of dimensionality. So let's look at what it means. So that this occurs in many areas of mathematics and computer science. So I'm going to make the very basic assumption of some locality in terms of the problem. So essentially the target function will be Lipschitz continuous. So if 2 points are close, then the target functions are close, okay? And for that, it is known that there's large literature on from statistics that the best you can do, okay, is so the best possible performance or the excess risk, okay, will be going to 0, okay, as n grows, but the power of n will be very bad in terms of d. It will be like 2 over d. Let's forget the d plus 2. It's essentially 2 over d. So this means that if you want to achieve an excess risk of epsilon, the number of points have to be exponential in d. Okay, this is one instance of the curse of dimensionality, and this is unavoidable. Okay, so this is the bad news, but this also very much like the no free lunch theorem. It's not very informative because this is a very huge set of problems, and so it's unavoidable unless you make some extra assumptions. Okay, and the goal of today is to look at those extra assumptions and to see if they can be leveraged automatically or not by algorithms. So we go over 3 assumptions: support of inputs, smoothness of S star, and the presence of latent variables. So let's look at them one by one and see how the algorithms I've mentioned so far, how they are dealing with those. So support of inputs, so I'll be quick. So in many instances, your data will lie not on the whole, will not cover all of RD or not a set with non-empty interior. Often you will get like data along a subspace or manifold. And so here, basic example of a manifold of dimension 1. And often data will lie in a space of dimension R, okay, in an ambient space of dimension D. So this has a strong effect on learning algorithms. So either you know how to identify this subspace, and it's easy if it is linear subspace, just do PCA. It's reasonably easy if you can do manifold learning, and at the end you replace the D in the right by the R in the right. So you're not anymore exponential in D, but exponential in R. So if R is much smaller, you gain quite a lot. But for most algorithms, you don't even need to give them the subspace. Okay, if you give them the whole data, okay, they will adapt to it and not find it, but they will do as if you knew the subspace. Of course, you don't get like computational gains because you don't project before running, but at least in terms of performance, it's not too bad. And most algorithms adapt to it. The second property is the smoothness of the prediction function. Okay, so I've assumed earlier on that the functions were Lipschitz continuous, which is essentially bounded derivatives, but you can go to higher order and impose that all the derivatives up to order S are bounded. Okay, and typically you would hope that if you have a smoother problem, it becomes easier. So here on the left, a hard problem where the target function is non-smooth, okay, not even if it's continuous, and this one where it is infinity. Okay, and you would expect that this is easier than that, and this is true. So you can show that the best you can do is not anymore dependent on D only, but you replace D here by D over S. So when S is 1, like before, you recover this. But if you have super smooth problems, when S is the order of D, then this becomes a constant and you lose the curse of dimensionality, at least to the power of n. So often you get like a constant in front of here, which could be exponentially dependent on dimension, but its dependence in n on the precision, you lose this bad dependence if S is quite large. So there's a large literature on this, and a very nice book by Bjorfi and colleagues. So typically it's hard to know in advance, okay, if you're going to have a smooth problem or not, okay, and some algorithms adapt to it and some don't, and I will show examples in a moment. Finally, last assumption is that the presence of some potential latent variables. Okay, so what do I mean by latent variables? I mean that I have X, I have D dimensions, but only a small dimensional projection is useful for prediction. Okay, so my data may occupy everything, but I just need a projection, okay, to do predictions. So the classical setup is variable selection. I only need like 2 variables out of D for predictions. It's all area of sparse regression, but it is not limited to taking linear projections on the coordinate axis. It can be any linear projections. And here, an example in 2D with 2 inputs, that this is a function with no latent variable. This is a function where there is like the y only depends on that axis. Okay, so this happens a lot in practice to have, underlyingly, you hope that only a few variables are useful. And what you hope is that you could replace D, the dimension, by R, okay, the often called the efficient subspace, and this is what happens, okay, for several techniques. You can replace D by R. So if you depend only on a small number of variables, then you don't pay the price of D. Okay, all right. So now we have some properties, okay, and the key here is that those properties are often unknown to the algorithm. I give you data X, Y. So for the support of inputs, okay, you could estimate it, but smoothness, to estimate smoothness of the target function, you have to solve the problem. Same thing for projection for the latent variables. Often, you know there may exist some regularity, but you don't know it. Okay, those are unknown. So of course, I focus on like RD, but you could imagine other type of properties if you work with like images and so on. So what we would like is to have some adaptive algorithm. So what is an adaptive algorithm? It's an algorithm that will benefit from these like properties, this reduction in rate, like replacing D by R, as we have seen earlier, or replacing D by D over S in the smoothness case. And this, of course, has to be done semi-automatically. And here, for simplicity, I'm going only to assume that with a proper choice of the hyperparameter, you achieve the correct rate. Okay, so how you choose that hyperparameter, you could do it like with fancy techniques from statistics, or simply do cross-validation. And I think this is what we would do in practice. So here the goal is you want that there exists a value of the hyperparameter for which the rates that I've shown above are satisfied for those techniques. So you benefit from the assumption, but you don't need to be given the assumption. Okay, you just need to know the existence. Typically, there's a cost of adaptivity, and hopefully only logarithmic. Okay, so for people doing a sparse regression, is very well known. You replace sigma square D over N by sigma square K over N. That would be the full adaptivity, but you pay a price of log D. Okay, and this is what we will have as well, but I'm going to not go into details of the exact cost of adaptivity. All right, so now who wins? Okay, so I'm presenting 2 classes of technique. Okay, essentially like local averaging, empirical risk minimizer with linear models, and neural nets. And so now I will go over them, and what will come out is that if you forget about optimization, and clearly you should not forget about optimization, but let's forget about it for the moment, then local averaging will be less adaptive than linear models and less adaptive than neural nets. Okay, and so let's look at that. So this looks like a superiority of neural nets. Okay, but we'll see that it's not as easy as it sounds because neural nets are hard to optimize. All right, so let's look at local averaging briefly. So it's known that it's adaptive to the low dimensional support. So if you data lie around the manifold, then if you choose a number of nearest neighbors shrewdly, like depending on R like that, then there's a nice paper by Samori Kpotufe showing that you get the optimal height. Okay, so this is nice. You get adaptivity to the low dimensional support, but that's it. you don't get any more adaptivity. So if your problem is super smooth, you won't benefit from it unless you use extra techniques based on local polynomial regression, but those are a bit harder to implement and don't scale well to high dimensions. So there's no adaptivity, okay? And for me, this is one of the reasons why they are used only in low dimensions, because you cannot leverage properties which may make the problem easy. All right, so now let's look at the empirical risk minimizer techniques. And for that, I'm going to focus on the single architecture that allows me to do both convex and non-convex optimization. So this is a one hidden layer neural net. So this is mostly for notations. I have my input X, my output Y equals f of X. I have some hidden neurons, M of them. So the M is the number of hidden neurons. The input weights are denoted with a B. It's a matrix, and the output weights is a vector, so it's A. And I'm going to consider the limit of overparameterization when M goes to infinity. Okay, so this is a goal. And those models are I will feed the model using like minimizing the empirical risk, which I will regularize explicitly to avoid the issue of implicit regularization. I have a square loss, but this will apply to any loss. And I add the classical L2 penalty, okay, squared L2 penalty on all the weights. And the algorithm, typically, you just initialize all weights randomly and just minimize using GD, AGD, Adam, whatever. Okay, you minimize. Okay. All right, so I will present the two regimes, okay, which are classical. The first, when you optimize only over the output weights, okay, A, this will be a linear model, and the kernel regime, and one where you optimize over all weights, which will be the neural net regime. So first, the kernel regime. Okay, so again, I'm going to minimize the empirical risk. Let me be precise on the assumptions. So B will be initialized uniformly on the unit sphere with a given radius, 1 over root m. A will be initialized whatever, because anyway it's convex. This is jointly convex in A, so it don't really matter how you initialize. And you can see quickly that it's a good all least squares, okay, penalized least squares, where with the feature vector, phi of x with m components, and the jth component simply the hidden neuron. Okay, so this is just ridge regression. So you can go back 20 years in time and look at what people were doing at the time. And it's known that for those problems, the kernel will essentially characterize what's happening. The kernel function is simply the dot product between two features at x and x prime. And here, because the features are essentially the hidden neurons, the kernel is simply the sum over all hidden neurons of that dot products. And because I've taken Bj uniform at random with radius 1 over root n, when I take the product and I remove the constants, I get 1 over n times the sum of the same things where Bj's are on the unit sphere. So at the end, the average 1 over n times the sum will converge to the expectation by the law of large numbers. And when n goes to infinity, you end up to the a kernel, which is the an expectation over that thing. Okay, so let me copy this here. So this is like a very classical, and this is those are two consequences. First, this expectation in that particular situation can be computed in a closed form, and this is true in many setups. When you do in the kernel regimes, whether this is like random features or neural tangent kernel, you can end up computing the kernel in more or less easy ways, and this is an easy way because I have a single hidden layer. And it is a classical random feature ID by Neil and Raimi and Recht, but here used in the opposite direction. So in those papers, at least the one by Ali, Raimi, and Ben Recht, you are starting from a kernel, and to avoid a high running time complexity, you will sample features, okay, with the rule that m is smaller than n. So they will use a small m, okay, and not an infinite m. So here we use it in a different direction. We want to understand what's happening when m goes to infinity. So we rely on this same ID, but on the opposite direction. So this has first some consequences. First, if you only optimize over the last layer, it's useless to be overparameterized and pay and burn the entire forest to have M go to infinity. Just apply the kernel trick, and you know in advance that F can be represented as a linear combination of kernel functions, and the unknown are becoming the alphas. Okay, so here, of course, if you do things naively, you have to compute the kernel matrix, so O over n square. So if n is 1 million, that's a problem. There are many techniques to avoid that, and I will refer to a nice paper by Alessandro Rudi and colleagues for that. Also, if you want to still have random features, we can characterize quite precisely the number of neurons that you need to achieve that mean field, that limit regime. And I refer you to my own work and the one of Rudi and Rosasco for that. So because, take home message, because it's all convex, everything is easy, can be fully characterized. So those are computational consequences, but I want to care about the statistical ones. So statistically, what you can show is that the space, which is the function space defined by this kernel, is a subordinate space of functions, so functions with derivatives which are square integrable, and the order of differentiability, like for all kernel space, is big. Okay, so the functions that you describe with that model are at least d plus 3 over 2 times differentiable. Okay, so this is like very smooth when d is very large. So when you run the algorithm, you don't need the target function to belong to that space, but the model that you consider is with smooth functions. In particular, all of your iterates will be super smooth. All of your estimates will be super smooth. So one thing that we need later on is a representation of those functions as with an infinite set of neurons. Okay, so you can see those functions as, so you replace here the sum of aj bj transpose x plus. If you have many aj's, you can take a continuum of bj's, and then you obtain, like a measure of neurons, and the kernel space ends up penalizing the square norm of the measure of our neurons. Okay, so the square norm is of course you want a Hilbert space, so you have to be a square norm. Okay. Right. So in terms of adaptivity, then it's also quite well known. So it's adaptive to low-dimensional support. A very nice recent paper by Ham and Steinbart on that. So essentially, if you data lie in a small subspace, then we benefit from it. Also, adaptivity to smoothness. So this dates back from Caponeto and De Vito. This is one very nice area where you can really adapt lambda to the smoothness, and it gets very nice properties, adaptivity to smoothness. And for example, if I take on the left a smooth problem, on the right a non-smooth problem, and I vary lambda, so here lambda is very big, 10, and I decrease lambda, 1, 10 to the minus 2, etc., and then I go from underfitting to overfitting. Okay, so here this is like strong overfitting. I interpolate the point, but I do very bad away from the points. And if I choose a good lambda, like that, let's say like this one, then I get reasonable predictions. Okay, and at the end, if I vary on the right the number of observations, and I plot the excess risk after having chosen the good lambda, it goes to 0. Okay, so we are learning. Okay, and in the log-log plot, the line has a different slope. For if you're non-smooth, the slope is not very steep, and if you're smooth, the slope is steeper. Okay, just to highlight the adaptivity to smoothness. So this is a positive aspect compared to local averaging. So when you say that kernels are glorified nearest neighbor, that's not true. Okay, so it does better than nearest neighbor because it adapts to more things than nearest neighbor. But it does not adapt to any form of latent variables. Okay, so if in the simplest case, you know that your F star depends on a single projection, it won't take advantage of it. okay? And one of the reasons, which is sometimes counterintuitive, is the fact that a single neuron, okay, is not in the subarray space. Okay, a single neuron is a ReLU, it's not differentiable, so it's not in the space. Okay, so at the end you're going to combine a lot of neurons, and when you take that expression, this one, you average over many neurons, and typically when you average a lot of non-smooth components, it becomes smooth if the mu here is a bit smooth. And because we penalize the L2 norm, we end up like smoothing the single neurons, and you end up with only smooth functions. So it's a bit counterintuitive, but this is what you obtain. All right, so now this was for kernels. Now let's go to neural nets, okay, for the remaining like 15 minutes. So now we're going to optimize over all weights. Okay, there are many questions that people have been asking. Okay, so let's consider 4 questions. So the limit when the number of neurons go to infinity, often called the mean field limit. Is it adaptive? Okay, the topic of the talk. How big M needs to be? So this is a bit unclear. And really, can you solve this problem of optimization? And this will be the main focus of the latest part of the talk. All right, so now we have this particular setup for which we can say a bit more things. So this is my prediction function. This is my penalty, which I made explicit to make things simple. And first, I can notice that I have some invariances. So if I multiply aj by mu j, and I divide bj by the same mu j, the product here is not changed. Okay, but the penalty is changed. So at optimum, I can take mu j to be the minimum of that with respect to mu j. And you can quickly see that the sum of those two terms with respect to mu j, has a fixed product. So the sum is minimized when the two are equal, and you can check that you obtain that sum. Okay, so the equivalent penalty is of that form. And now you can start things, nice things happening. You can reformulate it in a space of measures, very much like for the kernel case. So you take f of x will be a linear combination of neurons with some measure over the unit sphere now. And you can check that if you take mu being this, so you put a Dirac at the normalized bj, normalize the bj to unit norm, but you multiply the unit norm of bj, the norm of bj here. And if you take this integral, you can check that this for that, you're going to get exactly something like this. And the reason being that you take bj here, you divide by the norm, multiply by the norm over there, and you exactly get that integral. Okay. And why is it nice? Because now if you take the total variation of that measure, you recover exactly that penalty. Okay. So this is just like a very informal argument, but at the end, this is what you obtain. So you can reformulate this as the problem on measure, and when m goes to infinity, this is often called the mean field limit, where you're going to go from a space of Diracs to measures with density, and this is not new at all. Okay, I think this dates back at least from Bach in the 90s, and there are a sequence of works looking at it, and it's now quite common to consider that the overparameterized regime has a problem on measures. Okay, so we have a well-defined, this defines some function space. Okay, the set of f, which can be written like this, with this being finite. This is a function space, which is not a Hilbert space because there's no square over there. And the key difference compared to before is that the total variation is finite for Diracs. So a single neuron is okay. Okay, and I have some L1 aspects here. I have a no square. So I'm going to have some adaptivity linked to having L1 penalties. All right, so this is the exact same slide. So if you first, the approximation by finitely many neurons. Okay, so here, I'm going to be very brief here. So essentially, we have a function space. So if f belongs to the function space, it can be approximated by a small number of neurons. and otherwise it's kind of difficult, and you can have a very defined, very precise M. You can look at those papers if you want to know more. What I want to focus on is on the adaptivity property. Okay, adaptivity property, and let's look at the first support. Okay, so very much like the others, if your data lie on a small subspace, then it's fine. And the nice paper by Nakada and Imaizumi about this. For smoothness, you obtain the similar things as for kernels, and I can look at this paper if you want to get like all the details. What I want, the new thing, which is what I think is important and quite different from kernel, is that you get benefits of the L1 norm. So if you can optimize, and it's a big if, then you will benefit from presence of latent variables, of course, without the need to know them in advance. It will find the latent variables and adapt to it. So, for example, if you assume f is a nonlinear function of R projections, then you're fine. Okay, you replace D by R at the right. So you.
Francis, there is a question from the audience.
Oh, sure, go ahead.
Francesco, yeah, you can ask by yourself. Thanks.
Yeah, sorry, this is a bit behind the talk. It was really about the single neuron not being in the Sobolev space associated with the random feature kernel, right? So is this really about the fact that the preferred solution has a low L2 norm? Because, I can always think that if I draw randomly features, there's always going to be one that coincides with that neuron.
Yeah, but at the end, it's so let me go back there. I think it's a matter of low L2 norm, yeah. So okay. You at the end, yes, you're going to have. In fact, no. In high dimensions, you will never get the correct neuron. Okay, first, in dimension 1 million, you will. In dimension 10, if you sample,
you will get the correct neuron.
But what you can show is that you can approximate any function because that Sobolev space is dense in L2. So you will approach anything, including a single neuron, but that will take you a huge norm. Okay, so since you want to penalize, you want to favor low L2 norm solutions, to estimate a small, like a single neuron, you will need either a lot of features, M, okay, or a lot of observations.
Yeah, thanks.
Okay, let me go back there. Yeah, so I think, so here we are in fact, so adaptive, okay, you can show that if you have some linear latent variable, you're going to adapt to it. A key question is, what can you say with more than a hidden layer? Okay, so what you can hand wave your way around is if you get more layers, you could probably replace those linear functions by smooth functions. Okay, so if you have a first layer of, let's say, a kernel layer estimating smooth functions, then you can replace it by a complex function of smooth functions. And you can imagine doing this like recursively, but this is still like, I don't know, I'm not aware of any paper doing that. And I forgot to mention in the intro, I probably overlooked some references. So if I missed something, don't hesitate to send me an email about like the missed reference, I will add it. It's hard to follow all the literature. So just like a small experiments for adaptivity, this is in classification. This is done by with Lenaik Shiza. So we have a classification problem where the first two coordinates are where the action is. So those are the data in the first two coordinates, so well separated. And we add like noisy dimensions. And if we optimize about the two layers, kernel regime, about a single layer, sorry, kernel regime, this is an orange, so it takes for a while to converge. Whereas if you run a neural net where you optimize over all weights, you adapt to it more quickly. Okay, so it's small dimensions, but this is just to give you a hint on how it works. All right, so this is all nice. So neural nets are superior because, at least for that particular way of of characterizing performance because they're adaptive to everything, support, smoothness, and latent variables. But this is only true if we assume we can optimize everything. Okay, so let's look at the impact of optimization, and this will be more open problems than solutions. So what is the problem we want to solve? We have this empirical Rx minimization. Okay, so it's non-convex because it's convex in A, but non-convex in B because you have like the nonlinearity. And again, you initialize and you do gradient descent or any version of gradient descent. So there are two conflicting properties at stake here. So the first one is somewhat positive results. Okay, so I could have given a talk on global convergence of algorithms for that setup, and let me briefly mention what I mean here. This is joint work with Lene Shiza from 4 years ago, where we showed that if you let m go to infinity, okay, so then you get you take the gradient flow instead of gradient descent, so the limit of with vanishing step sizes, you convert to a flow on the space of measures, which is called a Wasserstein gradient flow, and for which you can show that if it converges, it has to be to the global optimum. So although you may have some stationary points, which are not global optimum, for that particular setup, this is the power of overparameterization. So the negative aspect of that result is that it's only qualitative. So we were never able to quantify how big or how small or big m needed to be. Okay, and we always fail, and I think there's a reason, which I will explain in a moment. And the reason is that it's very hard to overfit, okay, with a single hidden layer. So what I've shown earlier, that figure, this, try to reproduce a similar result with one hidden layer neural net, it won't work, okay? And I've asked that to many people, okay, and you need like a number of neurons which is like very, very large. And this is kind of weird. This is not true if you have more than one hidden layer. I don't understand why, but this is nice open problem. So let me then show what I mean by this, okay? And I call it it's not me, but other people call it the simplicity bias, and I have a reference in the next line. And so we have this result with Enaic, and others have shown similar results that if you have infinite m, then it converges. Then we provide some nice pictures and videos about like convergence for small m, and we take like a very simple problem, or take this problem in 1D, okay, with like 4 kinks, okay, so 4 neurons are enough to do perfect predictions. We know that if you take m being infinite, it should work, but even for m being 32, you already get like very good performance. Okay, so this highlights the possibility that there should be a result possible for having a small m and still preserve global convergence. Okay, so this is okay, but then you change a bit the problem and you put like a small difference, okay, here and here. You can try with m being 32 neurons, you can try the regular gradient flow, so gradient descent with a small step size, and you will not find it. So you can try to increase m, okay, and here I took m being 1000, still the same. I remember I took m being 10,000, it's still the same. Of course, if m is very, very large, it will ultimately converge, okay? You will get those exact true performance. But here, even for a very simple neural network where you generate data with no noise from like here, there is 7 or 8 neurons only, you don't find it unless m is very large, okay? And so here, there is super strong underfitting due to the bad optimization. There's a nice paper by Shah and colleagues calling this a simplicity bias, and this has been observed by several people, but it's still, I think, for me, not well understood. So maybe the last part is that you can overfit if you really want to. Okay, so this was, I played around and I was very annoyed that I couldn't overfit these neural nets. And so it's possible if you do things in a specific way. And one way of doing it is to optimize with respect to A in closed form. So what I mean by that, so if you take here, with respect to A here is these squares, okay? And if you are doing another convex law, that would still be like strongly convex. So it's easy to optimize with A in closed form. Then once you optimize with respect to A in closed form, you get a function in B. And on this one, it has a similar formulation as a measure-based problem. And on this one, you can get overfit. Okay, so I will not give you details, but you can start to do optimization and start to overfit again. Okay, and so on the similar problem, I take 128 neurons. So with a regular flow, it was not converging, and on this one, it starts to converge. Of course, downside that you will start to overfit again. Okay, so you may say that you may prefer to underfit or overfit. It's unclear, but at the end, it's not satisfying. Okay, so just saying that neural nets don't overfit naturally can mean that they underfit. Okay, so this is true for one hidden layer, maybe less true for more than one hidden layer, but this is to me a nice problem to look at. How do you make it not underfit, not overfit, but fit? All right, so let me conclude for taking like questions. So this talk, I tried to highlight adaptivity as a good property of learning algorithms, okay, that allows to differentiate between various classes of algorithm. Okay, so 3 types of adaptivity, and if you follow like the complexity of techniques, so local averaging is very simple, like no training, but it's only adaptive to support, like low-dimensional supports. Linear models, infinite dimensional, but linear models, so where optimization is easy, but easy, is reasonably easy. You get adaptivity on top of it to smoothness, and neural nets are more adaptive, but there is this optimization issue. So it's difficult, okay? So overparameterization is a way to overcome many of these difficulties, but it does not solve everything, okay? This is still quite difficult to understand, even in the simplest setup. And so often people talk about the funny thing is that people use the word bias as a positive thing. Like the implicit bias is seen as being something positive, but it can also mean that the simplicity bias where you tend to oversimplify. And sometimes it's okay, sometimes it's not. And to really, the goal is to go between this under and overfitting issues. So several open questions, which I didn't look at. Still understanding basic optimization for a single hidden layer with M being not infinite is still like difficult, okay? And of course, this is only for a single hidden layer. So of course, going deeper is important because it may make things simpler, okay? From what I've been told, this lack of overfitting is not as strong in the deeper networks. And of course, we want to go convolutional and adapt this to like images and so on. Thank you for your attention.
Thank you very much, Francis, for the great talk. Very, very insightful. And questions from the audience? Someone would like to ask a question?
I have one for Francis. So we observed this difficulty of overfitting as well. I think if we train for 30 million iterations, we finally would be able to overfit a regression network. But I was wondering, what do you think about whether a classification is a much easier task to overfit? Because you can imagine you don't really need to be very far on one side of a decision boundary in order to overfit a classification. And maybe some of this difficulty in analysis is because we are trying so hard to understand regression, which is much harder.
No, that's a good point, but I can imagine. I think here there's a strong bias in the community towards classification problem with a base rate which is small. Okay, if you take computer vision, okay, an image, the dog or a cat, it's not something in between. The uncertainty is mostly because the algorithms are not powerful enough. But there are problems, like in biology, where if you do diagnostic of cancer, it's not the base rate. There is a natural like noise, which makes it difficult to predict. And my feeling is that for problems with low noise, I think I would see there's not such an impact of not being able to overfit. But as soon as you have some noise, I would say that it's close to regression. I think to me, I tend to think that regression and classification with noise is quite similar. Classification with no noise is a very different beast. And what you observe, what you mentioned, that just need to be like, just to know a little bit of information to be in the correct side of the boundary, I think makes it different, makes it quite different. And this is why there's quite a surge of paper looking at these like perceptron or variations thereof when you have like those like perfect separation. So I think it's valuable for some problems, but not all problems in the world are computer vision problems. I think not the one which people care about. Okay, I will not, maybe at NeurIPS or ICML, yes, but this is a very biased subset of the world.
Great, thanks.
Yeah, thanks. There is an additional question from the audience. Yaim, would you like to ask by yourself with your microphone? It is written in the Q&A.
Yeah, I see. Okay, so maybe I can. Okay, so the question is, so here, what makes it like underfit or overfit? So here on the left, I'm just using plain gradient descent where I initialize always randomly, and I just run gradient descent. Okay, I'm not using PyTorch and TensorFlow, but my students have used PyTorch and TensorFlow with the exact same problem. You launch TensorFlow, you will get something like that. Okay. For this one, what I did is to simply take that problem. So you have a least square problem. Okay, and this is what I had worked on 20 years ago. Okay, on kernel learning. So this was the glorious days of kernels. Okay, where you could optimize over the weights. You end up a function of the features. Here's the b's, and you optimize b. Okay, and this is what I'm doing. I'm optimizing b directly, where whenever I want to call the gradient to b, I optimize out a. And so this is where, and then with a fixed b, okay, for the first iteration, that's important. The first iteration is random features because I initialize the b's and I optimize over a. So at the first iteration, since the b's are random, I'm solving the random feature problem. So at the first iteration, I can get something like that immediately, okay? And as I go along, okay, I have a video. If you go on my blog post, there is a video, I think. I forgot. I think there's a video where you see the same figure, but with a neural net. But as you go along, okay, you will select neurons and you get a similar figure with piecewise affine. Okay, you fit relus. Okay, so at the end, your function, if your function has a finite number of active relus, is going to be piecewise affine, and you get a piecewise affine interpolant. This is what you get. But you will never get this piecewise affine interpolant by just optimizing directly. You have to help the optimizer. I don't know if this answers your question.
Okay. We have two more questions.
Yes, the bibliography page, I can show it. And I think anyways, if you go on my blog, which you can find hopefully easily through like a search engine, the references are there, and probably I'll send the slides to Yehuda to put online if you want to. But I flashed the references. But I can do it now.
We have an additional question in the chat. Navid, you're welcome to ask by yourself also if you would like. But Francis, you can also.
Hi, thanks for the great talk. So I'm going to read from the chat. So I was wondering whether it's fair to say that we're able to avoid curse of dimensionality by having more structure on the distribution, but the curse is somehow converted into a different format, like maybe the time complexity of the optimization procedure, like to achieve the minimizer would be much worse than compared to before or something like that.
No, that's very good insight. I think so. Here, I think you have the so-called computational statistical trade-off, okay, which is has been around for the last 10 years or so. I think this is one instance of that, in that you to behave better in terms of prediction performance, adaptivity, okay, then you end up with a more difficult optimization problem. And here it's still unknown what that trade-off is between computation and statistics. Okay, so we know if you have infinite time, we know what the trade-offs are. Okay, but we don't know if you add the well-defined running time, which nobody really knows when you start to have the neurons to move. Okay, it's an open problem about what is the exact statistical computational trade-off in that setup. Okay, so what is unclear to me here is that do we still need to go all the way trying to understand the one hidden layer, or should we maybe try something deeper because things may be easier? Okay, so that's I think the two are interesting. I think going super deep, I don't think this is really necessary, but going to 3 or 4 layers, I think would be interesting to understand what the benefits are. And I think empirically, people told me that, yeah, it's not as bad when you have deeper layers, but I don't really understand why. And if you know references that explain why it's easier to optimize with a few more layers, I think I would be happy to have a look.
I see. Thank you.
Okay, great. Thanks for all the questions. And let's all thank Francis for his great talk. Yeah, thank you very much.
Okay, thank you. And enjoy the rest of the day.
Yeah, you too.